So welcome to this CP and ML talk. This is joint work with Brouard and Simon de gIvry working with me at INRAE. And Simon and I are also members of this Artificial and Natural Intelligence Toulouse Institute. This talk will be about learning cost-function networks from a set of high-quality solutions. So we essentially start from a training and validation set of high-quality solutions, and we leverage a recent scalable convex optimization algorithm from probabilistic graphical models to learn cost-function networks. And this algorithm is scalable, but it requires to set an hyperparameter lambda, and to tune this hyperparameter, we actually use the validation set. We take the cost function which has been learned by the convex optimization algorithm, and we use solutions from the validation set and a WCSP solver to check if the cost function network is able to produce good solutions in the sense of the validation set. So at the end, you get your cost function network. You can go through an extra optional step, which we call empirical hardening, where some of the cost function will be transformed into constraints, and you have your final learn problem. It is a cost function network. You can scrutinize it, you can add extra constraints if you have exact knowledge to add, and you can refine the criteria using extra cost function. If you stay with us, you will learn how we use graphical models to connect CP with probabilistic machine learning. You will also see how we can avoid this NP-hard loop, avoid spending too much time on it by simple tricks. And then the framework being defined, you will see how it can learn to play the Sudoku without knowing the rules, of course, and even starting from images with handwritten digits, as on the right, and how it compares with recent deep learning friendly architectures that learn to reason on the Sudoku problems. We also tried this on industrial problems. So it's a Renault car configuration problem. You want to learn user preferences and combine them with known configuration constraints to set up a configuration assistant. So let's start with graphical models. Graphical models are a very large family of mathematical models that all try to describe a function of many variables as a combination of small functions. In this talk, the first type of graphical model we consider are cost function network. They have a set of variable v, so at most n variables. Each variable has a domain, and the maximum domain size is d, and we have a set of cost functions. Each cost function has a scope S, which is a subset of v, and essentially maps tuples over S to an integer cost, which can be infinite. And infinity is used here to capture constraints. Infinite costs are non-authorized. And by taking the sum of all those cost functions, the small cost functions that have a scope, you define a joint cost functions, and minimizing this cost function is a so-called weighted constraint satisfaction problem. What do we exactly want to learn from high-quality solutions? So this is our target. We assume that we are given a set of variables v, finite domain variables, and we are given a set of assignments of those variables e, which we assume comes from an unknown distribution of high-quality solutions. And what we want to do in practice is to identify a pairwise cost function network M that can be solved to produce such high-quality solutions. And when I say pairwise cost function, I mean a pairwise cost function defined by cost tables. So you may have at most this number of cost functions, each described by d square cost plus extra cost for the unary cost functions. And given this, if there is one of those tables which is constant, you can ignore them, those costs, because they have no influence on the optimization problem, of course. The second type of graphical model we consider is this stochastic graphical model called Markov random field. Again, domain variables, functions, in this case, non-negative real functions. But the main difference is that instead of combining them by sum, we combine them by product. It gives a join function, which is non-negative functions over all variables, so tuples of all variables, and you can transform this into a probability distribution just by normalizing the joint function by a constant, which is, however, sharp p hard to compute. And it's easy to see the connection between MRF and CFN. Essentially, you have a product here. We add a sum for CFN. So using a minus log X transform, maximizing the probability in the MRF will be related to minimizing the cost in the associated cost function network that we denote as MR. And exponential minus X transform will go back to the original MRF, although we don't need this. And having the probability is useful because from this idea of probability, you can define this notion of likelihood. So assume you have a set of assignment E. You can define the likelihood of a model of an MRF M as the probability of the evidence you observe under this model. And so it's a property of the model, given data. And now you can try to find an MRF that has maximum likelihood for the data you have at hand. Essentially, you're looking for a Markov random field that will give maximum probability to the evidence you observe. And this is the so-called maximum likelihood principle, which is well known in statistics and has nice statistical property being consistent. And now you can see and exploit the previous connection. If we maximize the likelihood on the MRF, what does it mean on the associated cost function network? Essentially, it means that we will try to minimize the costs of the solutions we have in our set of high-quality solutions, which is okay. They are high quality, so they should have low cost. And at the same time, we will try to maximize the soft minimum of all possible assignments. The soft minimum cost of all possible assignments. So creating some sort of contrast between the training set and the rest of all possible assignments, which fits our previous target very well in practice. So we use a maximum likelihood. We use a more modern variant of it called regularized approximate max log likelihood estimation. Essentially, instead of optimizing the log likelihood alone, we optimize the penalized version of it, where we penalize the log likelihood by the L1 norm of all the costs which are learned. The L1 norm is just the sum of the absolute values. And the proportionality constant which is used to penalize is called lambda, and it needs to be tuned. And this kind of approach is known to avoid overfitting by essentially pushing non-essential costs to zero. So in several cases, you will see that you learn functions which have zero everywhere in their cost table. And as I said before, you can ignore those functions. So essentially, this algorithm simultaneously learns costs and scopes, which is nice. In practice, we use this recent algorithm. It avoids the Sharpie complete step by using a concave approximation of the normalization constant. It has nice statistical properties, and it provides a cost function network as output. The only problem that remains is selecting this lambda, this penalization factor. And for this, we use empirical risk minimization. So what we do is we use a separate validation set. We take an assignment in it, an observed high-quality assignment, and we assign a fraction of it in the learned CFN, and we solve this CFN with the WCSP solver. And we get a solution, and if the solution is identical or close to the expected solutions that you had in the validation set, then it's nice. Otherwise, it's not nice. And so you prefer lambdas that give solutions which are close to V. And this is how we estimate lambda. Obviously, this requires to solve a bunch of NP-hard optimization problems, and to avoid spending too much time in this loop, we simply use two tricks. The first one is to bound the optimization effort, and we bound the number of backtracks, 50,000 backtracks at most. And the second way to bound the effort we spend on this is to assign a larger fraction of V. Essentially, the larger the fraction of V you assign, the less work you have to do to complete it. And the gains are exponential, so it's easy to tune. At the end of this, you have your cost function network, and you can go through an extra optional step, which we call empirical hardening. Essentially, you will look to all the positive costs you have learned. You will check if they have never been violated in the training and validation set. And if this training and validation set is sure, reliable, then you can set the cost to infinity. And you learn constraint. And we apply this first on the Sudoku problem because it's a very well-known problem in CP, but also because it has been used as a benchmark by two recent neural net-friendly approaches. The first one is RRN, so recurrent relational neural net, with a very nice training, validation, and testing set. It's a large one, and it's split into 18 slices of increasing difficulties, or decreasing difficulty. So problems with only 17 pre-assigned cells or ints in the grid are very hard for human beings to solve, and up to 34 pre-assigned cells, which define simpler problem. SatNet is a more recent, deep learning friendly, differentiable approach that relies on a convex relaxation, also maxat relaxation. It uses its own training and test set, and they come from a website with very easy instances because the average number of pre-assigned cells is 36.2. So it's much simpler. And we use both the two test sets to compare either with RRN or SatNet. So how well do we do on the RRN test set? On the simplest problems, with 33 pre-assigned cells, we see that we start to produce correct solution around 2,000 training samples, and around, let's say, 6,000 samples, we solve them almost exactly. And if you look instead to the hardest problem, everything is essentially shifted to the right. So we start to solve them around 5,000 samples, and we almost solve all of them correctly at 9,000 samples. And if you go to 13,000 samples, we can actually check in the cost function network that the cost function network which is learned is correct, because we know the Sudoku rules. It has the exact expected scopes with the exact expected cost function, which represents soft differences. So we know for sure that the solution we get from this point will be Sudoku solution. And how well does RRN does on this very same test set? But RRN uses all its training set, so a very large training set. It also benefits from the fact that the scopes of the cost function are given to it. So it knows that there are functions inside lines, inside columns, and inside subcells or subgrids of Sudoku grids. And nevertheless, with this huge sample size and the knowledge of the scope, it never solves all the problems correctly, while this appears much sooner for our approach. Now, how well does SatNet does? So SatNet has its own test set. It's an easy test set, but essentially SatNet solves almost all his problems using only 9,000 test problems. With our approach, we are able to solve exactly all those easy problems using only 8,000 roughly samples, so less samples, better performance. And the solver which is learned at this step is very good on these easy problems, but obviously it's not that good on the hard problems. So you really have to take into account the problem hardness when you compare solvers. And then we went one step beyond. Following the track of SatNet, we applied our framework on images. And images with handwritten digits, which can be decoded by LeNet from Yann Lequin. And we know that LeNet has a 99.2% accuracy on handwritten digits. So if you just encode the pre-assigned cells, so the ints, as images, because in SatNet test set there is on average 36.2 ints per grid, you cannot expect that all the decoded grid will be exact, and actually only 75% roughly of those grids will be correct. So it's hard to think you can go beyond this accuracy because the input will be false in all the remaining cases. If you go to a more realistic situation where not only the ints are encoded as handwritten digits, but also the full solution is encoded as handwritten digits, then you have 81 cells that needs to be decoded by the net, and roughly only half of the grids will contain the net errors. So how do we do, and how does SATnet do on this problem? So SATnet, using only ints as encoded as images, does pretty well. It's a bit below the theoretical maximum accuracy, but it's not too bad. But PMRF, with almost the same amount of samples, actually is able to exceed this limit, just because we take the numerical confidence of LeNet as input to toolbar 2, and so when LeNet is very inconfident, we are able to correct his mistake. And actually, it's amusing to see that the Learn solver is better on harder problems. And this is just because LeNet makes less error, because there are less ints to decode. And because the solutions are still provided as numbers, not unwritten digits, you can do empirical hardening, and in this case you get an almost exact solver. It's not fully exact because LeNet errors can be sometimes not too bad, and you can end up with a correct Sudoku answer, but it's not the expected Sudoku answer in the test set. And finally, we tried something that would require a complete change of the deep learning architecture from SATnet, and SATnet did not try this. We encode both the ints and the solution as images, so it changes both the learning and validation steps. And in this case, we saw that 50% of our input grids are incorrect, but nevertheless, we are able to recover the exact answer on the test set in 76% because we can correct LeNet errors. We also tested this on this car configuration problem, so it's provided by Renault and Hélène Fargier. Well, you see the size of the problems. Actually, only 87 variables are decision variable. And even if there are large domains, most of the variables are Boolean. We have this number of constraints, maximum arity 12, provided as tables in XCSP format. And if you look into this, you can see that this van, because it's a van, has a huge number of possible configurations. And beyond that, beyond these constraints, we have a set of roughly 9,000 user configuration. So we tried 3 approaches on this problem. The first one uses PMRF and toolbar 2. We learn unary plus binary cost function. We use a tenfold cross-validation. And to give an idea of the CPU time, we spend 2 minutes per fold to process each fold. And the learn problem can be reinforced or not by configuration constraints, which are known, provided as input. We also tried a naive Bayes approach, knowing the partial assignment that the user provides, and a totally unrealistic oracle approach. This oracle will always make the optimal stochastic choice for the test set given the partial assignment provided by the user. So it will always choose for the next variable the most promising one given the test set. In practice, the test set is not known, of course. So it's an oracle that cannot be used in practice. And these are the results on this big problem. So you see the performance of this oracle. This is the number of variables which have already been assigned by the user, and this is the accuracy, or the precision. And you see that just below the oracle, we have our framework where we use both the learn CFN plus the configuration constraints. If you forget the configuration constraint, you end up here. And you forget instead the learn CFN, you end up here. So combining the learn preferences with the known configuration constraint is best. And this is it. So what did we see? Well, you saw this flexible learning framework for CP that we defined, which provides an understandable and editable output, which is very convenient. We also saw that even just a numerical solver, even if it uses integer costs, it's enough to interact with deep learning output. We don't absolutely require differentiability. Then, compared to SATnet, we think that the main difference we have with SATnet is that instead of using this convex relaxation randomized rounding step that is used to produce solution, we use instead a less scalable but anytime NP-hard prediction step, which is obviously more powerful. Actually, its power is adjustable, and we think it's the main reason for our improved result. And convex relaxation may well be the best we can do in polynomial time. So we now think that after having tried an NP-hard prediction steps and showing that it gives a good result without exploding in time because we use anytime solving, we think that people should now try NP-hard learning, and there are some recent proposals in this direction. So thank you for your attention, and you can fetch the slides below.